All right, good morning. So I did look a handful of places for the PowerPoint of this that is missing in action. I still have one place left to go. We were joking the other day about first world problems, and we have too many computers in our household, I guess, and every so often I'll write a lecture on an unusual laptop. And I'm always intend to save it to that hard drive in the sky, but sometimes it doesn't always go there. So we have to make do with me scrolling through an enlarged version of a handout. At least it's in color. So there might be some wonky scrolling here and there. I apologize. But we really do need to get through a conversation about plate tectonics. You guys know plate tectonics is happening. You probably even know that about Pangea, when the Earth was one big hunk of rock, and you know that it broke up into pieces after that. But what a lot of you might not know, and sometimes we don't even get a chance to talk about, was the fact that Pangea had to come together at some point. It wasn't just born as Pangea. It was, proto-continents, for lack of a better word, came together to make Pangea, and there were other incarnations before that. Rodinia, I always said Rodinia myself, was one previous sort of Pangea formation. And it's been, we have to assume, been going on for as long as the Earth has been here. So it's cool that you guys learn about Pangea. It's cool that you know what happened and that it's still going on. But we like to, just remind you at some point. And like I said, I'm not sure. I won't say I forget, but I forget if the slides really illustrate that well or not. And the fact that we are headed to some other future, grouping. As plates continue to move. I'm almost positive I have I'm sure it was somebody's master's thesis or doctorate, of projection of plate movement and what it'll look like, in the distant future if they keep moving the way they're moving and so on and so forth. So neat stuff. So not just a dynamic Earth right now, but always has been, and as long as we have internal heat, always should be. We talked briefly about Mars the other day in the stratigraphy conversation. And Mars, they feel, has lost its internal heat. And plate tectonics has ceased on Mars. So, again, studying the planets around us, we learn not only where we've been, but where we're potentially headed. I hope you guys, your teachers certainly could have said the words continental drift, but hopefully they said continental drift, and nowadays we call it plate tectonics. I always say, back when I was in school, and it wasn't too long ago, well, when I started teaching, it wasn't too long ago, but I was an 80s kid, right, so back in the 80s. I have to say I don't remember hearing the words plate tectonics till I got into college. In high school, my earth science teacher, I'm pretty sure they still talked about continental drift. Now, there's that old joke that school textbooks are ancient and so on and so forth, and that was really a lot more so, I think, again, back in my day. They have different grants and whatnot in place for you guys, even in the city school districts, not just the suburbs, that allow for textbook refreshments and so on and so forth. But I think it really just hadn't moved into that level of the curriculum yet. So we started, though, if you're familiar with continental drift, as you should be, hearing about it, to plate tectonics. It's really just a forming up of an idea. So we had Mr. Wegener here back in 1910, formulated this here idea. He wasn't the only one. All right, there were other people working on this, and as always, whoever provides the most convincing argument or the first to get to publish, whatever. Wegener went down. He also died on an expedition. That kind of helps, stick your name in memory of history. But one of the other guys was Seuss. Well, not the good doctor you guys know and love, but different. I think it was Edwin Seuss, something like that. He was also working along these lines. So Pangaea, all right, and then you might not remember the other two, Laurasia and Gondwana. Sometimes you see Gondwana land, but kind of just go with Gondwana. Laurasia was the northern continents, what we'd eventually call North America, Europe, and Asia. And Gondwana was the southern continents, Antarctica, South America, Africa. India used to be part of Africa, so we could throw that in there if you wanted. The subcontinent of India, they usually say anyhow. So here, a little seasick move. Sorry about that. I try to center this. Here is, no, that's too small. All right. Here is some little stop gaps. Print is pretty small probably for you guys to see in the back of the room there. So we got, up in the upper left-hand corner, we got 2.25 million years. Then they jump roughly 100 million years. Then right here, we're at 65 million years. All right. And the 65 million year one is, well, actually these two in particular in the middle are very interesting if you enjoyed studying dinosaurs as a kid, or even now still you may follow along. Because when you want to talk about, distribution of them, and, they're pretty widely spaced. Where we find these things. We got a huge chunk in North America. We got a huge chunk in China, and a handful smattered in between. There's some in South America, so on and so forth. Some in Europe, but not a whole lot. You see that, there was connected at one point. We don't even have to use the word land bridge. It was literally, one hunk of rock. What Gondwana, this sort of area down here, split off fairly early. I'm sure there were some connecting points here or there, but this was ripping apart right around, again, 135 million years ago. Dinosaurs were roughly, 200 million to 65 million years ago. So Pangaea was just assembled for a good chunk of dinosaurs, if you go back to the very earliest ones. And then as we go towards the end of the dinosaurs, you're definitely looking at a lot, much more separation, which allows for a lot more speciation going on and so on and so forth. So it's a neat study. It kind of goes hand in hand together. And then down here we have the current organization. Did I forget to mention Australia a couple minutes ago? Good gracious. How can I forget Australia? At any rate, so yes, our southern continents used to be attached to Antarctica. And if you look, they're fairly close. You got to watch. You guys know map projections are really warped. Globes give you a slightly better view, but map projections are kind of warped. So Wegener was right on the money, really. He looked at a number of things. He looked at when you line these continents back up, think about when you were a kid and you had those little woodblock puzzles. All right, maybe you had those, probably don't remember, but they might still be like up in your attic or something, or your little cousins maybe have them, brothers and sisters. But those hunks of wood that you would, either fit together and make one bigger puzzle, or at the very least fit into their own little forms. He looked at the continents in that manner. He was Wegener was a cartographer. He was a geographer, and maybe that gave him some unique insight. I don't know. But of course, the first and the stereotypical obligatory example is South America and Africa. All right, and the others sort of fell into place later. But the first big one that he was like, boy, that just looks like a lock and key, yin and yang, whatever you want to say. And when he lined them back up, of course he didn't line them up, but he looked at evidence and so on and so forth. Mountain chains connected together. Rock types connected together. The fossils in the rock types connected together. So in other words, not only was it the same rocks, but it was like literally the same environments because we were getting the same critters. And perhaps nowadays, those critters weren't even, well, a lot of them would be extinct, but wouldn't live in those environments that are currently there. And there was just so much going on. Plants as well, right? But, you're not going to really have the critters without the plants. But just so mountain ranges, rock types, fossils, everything lined up. What he didn't know is how or why. As I remember the story, he had the unfortunate luck of presenting his ideas to a group of geophysicists. And I don't know how many physicists you know, but they're practically as pain in the butt as the chemists are. But they're very, they have their rules of physics, by George, and that's what you've got. So I don't know if I have another slide here before yeah, no, so we'll stay here. We'll go back to this one, actually. So he's telling them his ideas, and they're like, Al, okay, how's this work? You think the continents are just drifting around in the oceans, floating from here to there? He didn't know. And because of that, it kind of, I doubt he got laughed off the stage or anything like that, but it didn't go anywhere at all. Remember, this is 1910-ish. So once we got some technology going, we had our wonderful submarines and some sonar and whatnot. Right around World War II, again, as I understand it, please don't take this as gospel truth here, but once we started scanning the ocean floors a lot more than we'd been paying attention to, we discovered, submerged mountain chains. We discovered trenches. We discovered all kinds of interesting features down there that led us to believe that, the ocean floor was not static. It was moving. And somewhere along those lines, somebody put together the idea that the ocean floors, the continents, they're sort of moving along in a conveyor belty fashion. And like I said, we had these new lines of evidence then. And again, right around in the early 60s, I want to say, we sort of merged over to this plate tectonics, solidified up as an idea. So, Wegener was long gone by then. Seuss was long gone by then. But they weren't forgotten. And here, 115 years later, still getting mentioned in Geology 101. So you already know this. And in fact, crust mantle core, right? Not just crust mantle core. You even know this. We took the crust and a wee bit of the mantle, just the upper bit, and we refer to that nowadays as the lithosphere. We've got the portion of the mantle just below that, the middle mantle, if you would, that we're going to refer to as the asthenosphere. And then that leaves that lower mantle that, I don't want to say we don't care about, But in this conversation, it may be the root, the origins of what we're going to talk about here in a couple minutes. But for now, conversationally, it sort of stays out of the picture. So the crust stays as the crust. They've really subdivided the mantle into 3 portions, okay, because we've attached one to the lithosphere, to the crust to make the lithosphere. We have the asthenosphere, which is the middle, and then we have that lower mantle. And then outer core, inner core. You may not, you probably won't see the layers of the Earth diagram on test 4, but it will definitely be making an appearance on the final. So if for some reason you mangled that on test 2, I think it was, take a look at it before you get to the final. I believe we even talked about this. This goes back to that everything you wanted to know about the Earth but were afraid to ask conversation that we had, several conversations. All right, we talked about the Moho line or the Moho-Rosich discontinuity, where we started learning, again, from the 40s, 50s, 60s, we learned a lot of this information, unfortunately through exploding atomic bombs, all right, but then also paying attention to earthquakes and whatnot. We learned these seismic waves, and you'll hear more about seismic when we get to earthquakes, which is why I really needed to have this plate tectonics conversation so we can get to earthquakes. So you hear much more about seismic, this, that, and the other thing. So again, just review at this point. If you felt I did not address your questions about the Moho-Rosich discontinuity, please refer to your notes from the Investigating the Earth lectures. I'm still not going to hold you accountable for these numbers. Just understand that the continents are thicker than the ocean floor. I think you could have figured that one out because we are above them. But and also they float at different. The ocean floor does sit a little lower, hang a little lower in the asthenosphere than the continental crust does, but even still it's thicker. All right. You probably saw this back in the day or remember seeing this. Again, still not responsible for the speeds, the depths, but basically what happens was there are little sound waves, okay, right there, sends out a shock wave through the Earth. It travels at one speed through the solid rock. It travels at a different speed through the molten rock. They were able to do a little mathing and figure out where that boundary was. That's all it is. So why did we review all of that? We reviewed all of that because the theory of plate tectonics needs it. And you did, again, hear a little bit of this at the end of the Investigating the Earth conversation. The lithosphere is broken up into pieces that we call plates. There are 6 or 7 large plates, dozen small ones, all right? And these plates float in this asthenosphere that we talked about, okay, kind of like ducks on a pond. Now, if you would conjure up an image of one of those little puzzles where you slide the squares around in, so you've got a square, and then there's, I don't know, let's say 16 squares in there that you slide around and you try to make an image, and there's only like one missing square. You all know what I'm talking about? Okay. You get the idea here that these aren't like floating truly like ducks in a pond. They can't just float off wherever they want. Again, the oceans and the continents are attached or at least bumper to bumper, all right? So that's not what's going on, which leaves you, okay, there's not a whole lot of room for these things to move. How are they moving? Well, and that's where I told you we had these mountain chains and we had these giant trenches. That's where they come into play. And we will get to those eventually. But it's sort of predetermined what direction everything's going to move for the most part. Because, again, there's not that much room to move around. There's no free space even like in that little slidey puzzle. Okay? Keep going to hit the space bar, which won't do a darn thing. So here's those lithospheric plates. We told you there were half a dozen-ish large ones. This picture does wrap around, so the green and the orange you see on the right-hand side is the same green and the orange you see over here. So we'll just start over here. We've got the African plate. We've got the Eurasian plate. We've got the Indian Australian plate, the Pacific plate, North American plate. Roughly lines up along as continents, but not entirely. All right. And we got the big old Nazca plate here. It's probably the smallest of the big ones, as it were. So let's see. 1, 2, 3, 4, 5. I guess we're counting the Nazca as number 6. And you got Scotia. Oh, I forgot. That's the big one. I knew there's another big Antarctic plate. I was just thinking that was all ocean there for a minute because it's blue. Silly me. So 1, 2, 3, 4, 5, 6 are our big ones because Nazca is usually not considered a big plate. So yeah. Arrows here are implying movement. All right. And we've got some different types of boundary here. They might look like weather fronts to you right now. We're never really going to learn the symbology, but we will learn the different ways that these plates can interact. Did we not say that? I don't know why that's there. So those plates are the ones that are floating on the asthenosphere. In case that was unclear. I just mentioned this in passing a couple moments ago. All right, the continental lithosphere sits higher on the asthenosphere than does the oceanic lithosphere. That's because granite and basalt, two igneous rocks you ought to remember, have different densities. Continents are made, I know some of you are still writing this down, so I'll leave it there for a minute, but the next one has a slide. Continents are made of granite at their core. Obviously, at the surface, there's a huge amount of sedimentary rocks, okay? But underneath all of that, the core of the continents is granite, while the oceans are primarily made of basalt. Again, near the continental margins, shorelines, if you would, tons of sedimentary rock piling up because, well, all the sediment washing off of the continents, okay? This will be important soon. So again, they're both igneous rocks. Continent is granite, comes in at 2.7 grams per cubic centimeter. The ocean is made up of basalt, which comes in at 3.0. Again, not numbers you need to remember, but do remember that basalt or oceanic crust is more dense than continental granite is. Because again, that will be important. What are you signaling with your hands there other than squishing? Well, yeah, sure. So why do we care about plate tectonics? Well, we care about plate tectonics because it is responsible for much of the stuff that's going on in the world. And a few things I haven't even mentioned on here. All right, it is responsible for the majority of the earthquakes on the planet. Volcanoes, the mountains, again, not all, and of course, the current, past, and future location of the continents. There are some earthquakes, like in New York State or in Ohio, that are nowhere near plate boundaries. They're just old breaks in the rock that sometimes happen. There are a few volcanoes that aren't anywhere near plate boundaries. We talked about the Hawaiian Islands, if you recall. But again, the majority. There are some mountains that weren't caused or formed by two continents smashing into one another. The Rockies are a great example of that. But many of them are. So again, we've got our plates, many smaller ones, and they move anywhere from 1 to 18 centimeters per year. At roughly 2.5 centimeters to the inch. I know a lot of us don't think in centimeters. If it were just 2 centimeters, we'd be looking at 9 inches. So we're going down 6.5, 7 inches a year. Okay. Which is, arguably speaking, a decent amount of space. Put it into the span of the Atlantic Ocean? No. Okay, or the Pacific? No. But for a hunk of rock thousands of miles wide to move, 7 inches every year, that adds up, especially when you've got the amount of time that we've got. If you recall those arrows you saw in a little while ago, they move in different directions. Again, not to get ahead of my slides, but this is one of the areas they're still working on, looking into exploring. North American plate is moving, we'll just say west right now. I think it's Pacific that's moving northwest. So North American plate is moving west from the middle of the Atlantic Ocean where it starts all the way over to the west coast of North America. That hunk of rock is moving westward. Then all of a sudden, as we get to the Pacific Ocean and all the way across to the east coast of Asia, that hunk of rock is moving northwest, and so on and so forth. So they're trying to figure out why it would change. You could just sort of go with the whole inertia thing. It bumps and it gets bumped in one direction. It keeps moving. But again, it's not like there's free space for these things to float around in. So there's a little something more going on. And I think they think so as well, or it would have been figured out by now. So again, here's those directions. Yeah, so North America, good, I did guess right, is moving due west. Pacific plate's moving northwest, while Europe and Asia's moving southeast. Okay, and that sets yourself up for some troubles. If you're familiar with any of the names of the islands in the Pacific Ocean, they're almost always having something horrible going on over there, but whether it be earthquakes, volcanoes. Same with the East Coast over here, Japan in particular. Okay, and it's just two boundaries that are just interacting in a very bad way. You're familiar with the West Coast of North America. We already introduced that to you guys back with volcanoes. And so you've got your San Andreas Fault labeled here. All right, and that is Pacific plate is sliding by the North American plate. And just a wee bit of California is on the Pacific plate. The rest is on the North American plate. A little bit, that Baja California that sticks down there, the Baja Mexico, is attached to the Pacific. And of course, many other places as well. We talked about the Mediterranean as being not a particularly great place. You see here we got a line going right through there. So, all right, anywho. So, I don't want to say at the moment here, but in general, there's three ways that these plates can interact. They can be moving towards one another. They could be moving away from one another, or they could be sliding side by side one another. Right? Things can either come together, pull apart, or brush along next to one another. And depending on which way they're interacting, and what type of lithosphere you're talking about, whether it's continental or oceanic. You get a handful, and these you guys do need to remember, you get a handful of different products, so to speak, results. And, of course, there's vocabulary attached to each of these. And again, this movement causes earthquakes, volcanoes, and mountains to be built. All right, so the vocabulary words. Convergent, divergent, and transform. These are types of plate boundaries. I suppose, before we get into the types of plate boundaries, it might not be a bad idea to remind you what a plate boundary is. What we mean, if you're not entirely clear, this is one of those seams. Okay, this is where one plate ends and another plate begins. These are those interaction zones that we're talking about. So convergent versus divergent. Which one is, remember we told you we had three things. Things can come together, they can pull apart, or they can slide side by side. Convergent, divergent. Which one's which, you guys? All right, convergent is come together. So what does that leave for divergent? Somebody else. Yeah, pulling apart, tearing away. You're diverging. You're converging. Words you might not use in everyday language, but you're familiar with what they mean. All right, and for once, they mean the same thing in here. So convergent plate boundary, you have two plates coming together. Divergent plate boundary, you have two plates pulling apart, which means that transform must be the sliding side by side. Not sure why they came up with transform for a word there, but so transform is the side by side. All right, now as I said, we're going to subdivide these. So we're going to talk about three areas where you have convergent activity going on. Remember, we have two types of crust. So we're going to talk about the way that can work is basically three different ways. You can get ocean on ocean, continent on continent, and of course, continent on ocean or ocean on continent. Either way, it's the same thing. So three ways to deal with this. You follow? You will see each of these again, so I apologize if you're still writing. All right. Continent to ocean has a special vocabulary word all for itself. It's called subduction zone. We mentioned it briefly. Well, actually, we spent a decent amount of time on it when we talked about volcanoes. We talked about the Ring of Fire, the west coast of North America. And hopefully what you recall is that the ocean plate is getting pushed underneath the continental plate. And along with that rock material going down, there's a whole lot of water. Remember this conversation? We talked about, throwing stuff into a fryer. So that's called a subduction zone. Now you are responsible for that term. I don't remember if I held you responsible for it during volcanism. All right. The reason that this happens, the reason that this works is, again, you'd think that the mile high of water, the ocean on top of that rock, the ocean floor, would be reason enough for it to, not rise up and overtake the continents. I'm with you on that one, okay? But they still want to point out that, basalt is not lighter, necessarily less dense. It's the proper terminology. And it loses in that collision, okay? It loses that battle. It gets subducted. It gets subdued. Whatever you want to say there. And hopefully I took a moment to point out back then. If not, I'll do it again now. I'll do it now or again now. That's really the reason that we have the oceans where we have the oceans and the continents where we have the continents in the first place. All right. If you go back to, we just actually talked about this semester at any rate, we just talked about a little bit of the hydrologic cycle, the water cycle. And we told you that the earth cracked open, all the steam came out. It condensed and fell as rain to fill up the oceans. Well, just like nowadays, that water would flow to the low spots. All right, the continental plates were already sitting a little higher than the oceanic plates. So there was already that disparity, if you would. So the water flowed down to the oceanic plates. The weight of that did push those down, which buoyed up the continents even more, increasing that difference. So, just a little reminder. So continent to ocean, we get subduction zone, and as a result, we get typically volcanoes. Now, when two oceanic plates meet, we don't have a special vocabulary word for it, thank goodness. We get trenches, and we all know what a trench is. It's a ditch, right? All right, well, they call them trenches. So, two oceanic plates, and for those of you at home, I'm sort of like smashing my hands together here. When they meet, both of your fingers go downwards, kind of like the opposite that they would face if you were putting your hands together and praying or something like that. Okay? Saying thank you, thank you, thank you to somebody. So, my hands are going downwards. So, those two plates come together, they go down. All right? And that creates what we call a trench. Very famous trench, if you pay attention to such things. Very famous trench is the Mariana Trench. All right? We have, I don't want to say explored the heck out of it, but we've certainly been down there a lot. There's a lot of neat things going on down there. That's where we talk about those giant tube worms and black smokers, and there's a whole nother ecosystem down there that runs on chemosynthesis instead of photosynthesis. All right, very, very neat world down there. Very, very deep, very, very hard to study. I think I mentioned James Cameron made a movie about it. I think it went straight to IMAX and then it hit the regular theaters probably 5-10 years ago at this point. Challenger Deep, I want to say it was called, something along those lines. You type in Challenger Deep and James Cameron, you'll get the right movie. Very cool. Very cool indeed. It is the deepest place on the planet that we currently know about. We also have another feature associated with trenches, and those are island arcs. Island arcs are surface features. It's a chain of islands. You might know the word archipelago, okay, archipelago, however you pronounce it. But island arcs are a chain of, in this case, they're volcanic islands. That's one of the ways we realize what they are. And sometimes they're just drowned mountains, you know. You get little bits sticking out here, and they look like a chain of islands. These were volcano mountains, though. Instead, they grew. And the best example for most of you would be the Aleutians. All right, they're up off of Alaska, and they curl around to, Russia, we'll just call it. Okay, northern Asia. This was that land bridge that you may have learned about back when the ice sheets were prevalent. The ocean was lower, so these were more exposed, and it was a lot easier for not just critters but people to get across it. And I always wonder, what we just said, there's a whole bunch of ice there. Wouldn't that be blocking it? Apparently not. The glaciers, I believe, tended to stay east of the Rockies, leaving the west coast fairly, free. So they came across the land bridge and down the west coast. That's why you see a lot of similarities, not to pull in sociology here, but it's all connected, between like the Pacific Island cultures And then if you ever looked at the natives of northwestern North America, you see very similar art, okay, and just everyday objects kind of stuff. So neat stuff, neat stuff. So trenches. Here's our trench systems. All right. We got a couple little ones over in the Atlantic. This one over here, Puerto Rican trench is important. But this one over here that they chose not to name, both of these caused some trouble in the Caribbean islands. Okay. There's a handful of volcanoes over there, and we do tend to see some earthquakes as well. But the big one, again, more or less works the north and the west side of the Ring of Fire, okay? Pacific Ocean here plate. So we have the Aleutian Trench and then down along the east coast of Asia. And it's a good bit off. All right, but remember our conversation about the subduction zone. All right, you don't necessarily see the problems right on the plate boundary. Sometimes they're manifested a little further off. When we're talking about, of course, island arcs, they are directly above the trenches. Don't get me wrong. But over here, we tend to see a bit more deferred actions. And again, the Pacific Islands are just a mess. They really are. There's so many. One of the biggest ones that comes to mind was the over here in Java. Back when I first came to town here, I think, early 2000s. And there was a horrific earthquake and tsunami a day or two after Christmas. And again, I don't know what religion they are. They may or may not celebrate Christmas. But it was, just talk about horrible timing kind of thing. Just immense devastation on Java. So it's they're sources of trouble, okay? They're not just, they make island arcs. That's cool. There's still can be some negatives all along the coast of South America here. We see it as well. And again, you'll see why we care in a couple minutes. So trenches come from ocean to ocean convergence. Continent to continent convergence. Continent to continent, instead of my hands coming together and going down, they're going to go up. Continent to continent is your traditional really, really slow car crash, okay? Everything gets all crumpled up. And we get, the Himalayas. We get the Alps. We get the Appalachians and the Adirondacks. I've learned over the 20-some years I've been here not to say that the Adirondacks are part of the Appalachians. You guys get a little edgy about that. They are, though. But whatever. They are, fairly distinct geographically nowadays, but they're similar origins, same time, so on and so forth. So the Appalachians, that whole stretch along the east coast of North America came when Pangaea was coming together. All right. So when the parts that would be Laurasia, North America, and Europe smashed together, all those hundreds of millions of years ago, they crumpled up the Appalachians. Okay. And again, not belittling them, but if you've ever seen the Rockies, you'll be like, oh my God, these are mountains. It's because the Appalachians are 200 million years older than the Rockies. Okay, that's a lot of weathering and erosion. They are the great-grandfathers. Okay, and the Rockies are, like 20-year-olds, to put it into humanistic terms. So that's the difference if you've been lucky enough to see both, and I hope you get a chance to one of these days. They're vastly different. Okay, that's the really big reason. Himalaya is the tallest and fastest growing mountain chain in the world. That's between India and Asia. The Alps, I don't know too much about the Alps, but they're pretty. There's Swiss Alps, Italian, German, they're over there. But I don't know much about their formation. Probably quite similar to the others. Well, they're under continent to continent, but So of course they're similar, but I don't know the time period, I guess is what I'm saying. All right. Did we cover all three? What did we got for? We got continent to ocean to ocean, and continent to continent. Yep. So we covered all three for convergence. We do not have all three for all of these. Lucky for you guys. Divergent. At the moment, we only have two going on. We've got ocean to ocean divergence happening, and we've got continent to continent divergence happening. Ocean to ocean divergence gives what we call a ridge. We'll explain that in a moment. And continent to continent divergence gives us a rift. We'll explain that in a moment, because you're going to be like, wait, this sounds exactly like mountains and trenches. It is, but we call them different things because it's a different type of formation. So what happens when two oceanic plates pull apart is that it allows the mantle to seep up through. Okay? We've got one of the biggest, longest, tallest mountain chains on the planet right now because of ocean-to-ocean divergence. It's called the Mid-Atlantic Ridge, and it runs essentially, from the North Pole to the South Pole practically down the Atlantic, as the name would imply, Mid-Atlantic Ridge. All right, pokes out here and there. All right, Iceland. Right? Where's that spot that they stop to fuel up when they're going from North America to Europe back in the war there? There's, no. There's a small island off of, no, way north, over much closer to England. But at any rate, pokes out a handful of places. The Galapagos are another one. All right. So any of these random, many of these random islands up and down the Atlantic are all part of this mountain chain. They're that exposed. Many people think that Atlantis, our fair departed friend, would have been one of these islands as well. If you read back to the way I think it was Plato described, related the information about how Atlantis was destroyed, it sort of fits the idea, or it fits the method that one of these islands would, explode and fall into the sea under, because they're volcanic. Iceland, for example. So, thought you had a comment. So, ridge is a mountain chain, okay? And there's a handful of places on the planet. This is, the big primary one that we always talk about. Continent to continent, on the other hand, you're further away from the magma, ideally. So, when it rips open, you get a rift, which is a tear, okay? You might have a rift in your friendship with one of your friends. This is just a rip in the rock. We were all excited. We were on field camp. I haven't told you too many field camp stories. It's probably better that way. But we were out in the Sangre de Cristo, the Blood of Christ Mountains in New Mexico, and we were going to see this rift system. And we're like, oh, yeah, I don't know if we expected, to see the gates of hell, or I don't know what we were thinking. But so we drive. We pull over to the side of the road, and the teacher's like, We're looking around. We don't see any lava, any giant cracks in the earth. It was a valley. Okay? It was a valley. And I won't even say, it was a valley and there wasn't a river there. But you know what? It's a low spot now because it's a valley. Guess what? It made a river. But it's a valley that wasn't created by a river in the first place. And, but, of course, much more so we knew, all right, this is where there was two continental plates pulling apart at some time. So yeah, rifts, with all the sedimentation when they're at the surface like that, they fill in. They don't look much different. Same thing when hopefully we'll get a chance to talk about glaciers in here. And we're going to talk about these, huge things of ice gouging through the landscape, carving out, moving millions and millions of tons of rocks. You can say, yeah, that's a valley. All right. The only difference is it's U-shaped instead of V-shaped. So, anywho, so continent to continent, when it pulls apart, it does leave a tear, a hole, okay, as you would expect. Unlike the ocean to ocean, when it pulls apart, it does fill up with lava, magma, and it just piles up. So now we're looking at the ridges. Remember a little while ago we showed you the trenches, all right? And I have yet to, let's see, did I put it in here? I did not put it in here. I need to make one of these semi-transparent and one of them a little darker because I have always wanted to stack the rift slide, the trench slide on top of the ridge slide. Because what this gives us, these ridges are where new ocean floor is being made. Every moment of every day, magma comes to the surface and adds. And this is one of the things we found out when we were going down and exploring with our submarines. We're like, oh my God, there's all this fresh ocean floor being made. We didn't know about the trenches yet. So we're saying, okay. And you guys think we were going back a lot in history here. So we hadn't necessarily been able to get up in space and, measure things as accurately as we were now able to do, so on and so forth. We're like, so the Earth's getting bigger? If we're constantly adding ocean floor, this thing has to be expanding. That's where the trench system comes in. The trench system is destroying crust. It's going back down into the Earth. So we have movement from the ridges to the trenches. That's the conveyor belt I mentioned so long ago. All right, it really shows when we're in the Pacific here. We're on the east coast of the Pacific. We've got crust being made. On the west coast of the Pacific, we have crust being destroyed. That, I think, allows North America to push through this way as this motion is going. It's sort of just a general, oh, there's some room here. Like you're in a crowd waiting to get in somewhere. And once, there's a little break in front of you, you and the people behind you and around you get to move forward just a little bit. I think that's a lot of what's allowing North America, as it's being pushed up here by the Mid-Atlantic, okay, as this is all moving this general direction. But, again, the smartest minds in this area are working on it, and they still haven't figured it out. So, I'm just here surmising. But, yeah, in an ideal world, we would see, again, the trenches and the ridges superimposed, and you could really then see the movement there. And I suppose maybe there's even that diagram exists out there. But and we see Iceland here, by the way. Yeah, and Greenland isn't really part of that. We came up with Greenland earlier. It's a different hunk of rock. I think if we took the sea level back down, we'd see it connected through up here somewheres. But again, don't quote me on that one. I know Greenland's been in the news a lot lately, but geologically speaking, I haven't paid that much attention to it. And also, one more reference, when we went back to the very beginning, back in the very beginning of class, we talked about the Earth cracking open, and I said, picture that baseball with the seams on it. All right, that's these guys right here. These are those seams we talked about so long ago, that stitching on the baseball. It's your ridges and your trenches making those basic plates. And from there, more breakage occurred. All right, we got one left. Transform boundary. Transform plate boundary. We're going to talk about continent to continent. All right. I want to say, and I'm pausing here. I'm hesitating. That we can pretty much have these anywhere. And I think we do. But an important one for us, a recognizable one for us, is in the example of the North American and the Pacific plates. I mentioned this a little while ago. All right, the majority, north of San Francisco
is, which isn't probably arguably the majority of California, but north of San Francisco is attached to the North American plate. South of San Francisco is attached to the Pacific plate. All right. And again, the North American plate is moving due west. The Pacific plate is moving northwest. And that does create a tearing. You don't hear it so much anymore, I don't think. But back when I was growing up, there was, oh, California's going to crumble into the sea. No. Well, I mean, a little bit of it maybe. But more so, it's just going to separate. It will become an island at some point. Okay? There'll be a channel first and so on and so forth. I don't think it's going to happen in one big event. It's going to be something very, very slow. And we will, probably knowing us, try to build bridges over it. Bridges that can withstand that slow shifting there. If we were smart, we'd just count on ferry traffic, but that's not very effective for, millions of humans. So we'll probably try to build some expanse over it. Because again, in the bigger scale, the bigger picture of things, it is a rather slow movement. Remember, centimeters to inches a year. But still, a lot of these bridges, 50, 60, 100 years old, that adds up for torsion and whatnot. I might have just made up a word there, but you know what I'm trying to mean. So that's a San Andreas fault. A fault, as you'll hear when we get to earthquakes, is just a break in the rock. Okay? And there are certainly others. Certainly others. This is just one that, again, is for, as Americans, that we are most familiar with. But you could get this side-by-side breaking in a lot of situations. All right. I just want to scroll real quick, see how many slides I have left, because I've been talking a long time, but I don't know that I have enough to leave. Yeah, I don't. It's a good thing I didn't call it a day. I don't know if I have enough to leave for another lecture. All right, so just to rehash real quick, we had three types of interactions. We had the side-by-side movement. We have the two plates coming together. We had two plates pulling apart. We have two types of crust. And depending on which crust is doing which movement, you get a different feature. You guys do need to remember that. Ends up being 6 or 7 things. I think it's 7 things. Okay? Roughly. And it's a good chunk of questions on test 4. So, what's up? And I'm really surprised it says the last slide. I should have some sort of diagram here, and I don't. It's weird. So we told you that Wegener didn't get very far because he didn't have a mechanism. All right? They think they know why it works. Now, they're pretty sure, I suppose. Again, the finer points, but the general idea is there. And that general idea is called mantle convection theory. Mantle convection theory is very, very simple. It's a lava lamp. Okay? I know not everyone has sat and stared at a lava lamp. You ought to. It used to be you'd have to go to Spencer's to see a lava lamp. I'm sure they're in other stores nowadays. You may even have one at home, or your folks might have one in the basement. I want you to get it this weekend, borrow it. You're home for Easter, whatever you're doing. Turn it on, clean it up first, turn it on, and stare at it for about half an hour. For those of you that haven't ever done this, I'll remind you what's going on. There's going to be a little hockey puck full of goo at the bottom, and then some sort of water. And most importantly, a light bulb. All right? This is actually a grand physics experiment. They're amazing. Really, really mindful is what they turned into, how silly they and cliche and whatever they are. It's an amazing experiment. So the light bulb doesn't just make pretty colors on your walls, all right, and pretty shapes. It is a heat source. So this is nothing that's ever going to turn into an LED. You're not going to find an LED lava lamp or a fluorescent lava lamp, they don't put off enough heat. We need that heat from the good old-fashioned incandescent bulbs. And that heat slowly warms up that hockey puck full of goo, and what will happen is parts of it will break off. And the first time one of them, kind of goes up, ooh, look at it go. And this little blob floats up. Well, what happens then is, guess what? Eventually that little blob comes back down. Why does that little blob come back down? The little blob comes back down because it has cooled off. And it goes back down to the other pile of goo. And at that point, you've got stuff going up and down and up and down. All right? What's happening is this stuff is expanding and contracting, changing its density due to temperature changes. As I said, it's really huge concepts behind it. Which is why they tell you don't leave this on for X number of hours, because what happens is you warm up eventually that whole column of water, all of your goo, and you screw up your temperature differential. All right? You are now constant temperature all the way through it. Oftentimes your goo can break down, and sometimes it never goes back together again. Usually it does. Because again, stereotypically, think of the people that are watching this. They tend to be a little forgetful, right? And they leave their lava lamps on too long. Most of them go back to normal. But they do, just everything floats at the top because there is no more temperature differential. That goo cannot cool. So, why did I just tell you about lava lamps? Well, because we need to talk about lava. No, actually magma, because we're inside the Earth, right? So where's our source of heat? Our light bulb is the core of the Earth. So remember I told you we weren't exactly sure where in the mantle this all starts, okay? The version I like best, and I think it's the leading version still, is picture gears, all right? And down at the very bottom of the mantle, we've got very big gears. And in the middle mantle, we've got smaller gears. The big gears turn the smaller gears. So what's happening down there is the magma is heating up from the core, and it's lowering its density relative to the magma around it, and it floats up. As it cools off, it sinks back down again. This creates what we call a convection cell. Nowadays, just about everyone's got a convection oven sitting on their counter. When I first started giving this conversation, that was only things you'd find like at fast food restaurants and big restaurants. Convection ovens cook things really quickly by moving the heat around. All right? This is also the basis on which your house is heated and cooled. Remember, warm air rises, cold air sinks? Remember that? It's the same idea. You've got your air conditioner vents near the ceiling. You have your heater vents near the floor. Second floor is hotter than the basement, and then the basement's even cooler and all that. All this stuff, it's all convection. All right? It's all lava lamps, man. It's crazy. No, I'm kidding. So, at any rate, but so that sets up a wheel, if you would, a conveyor belt wheel. Okay, a couple of them probably down in the lower mantle. Well, that does the same thing, but at a lesser scale in the asthenosphere, the middle mantle there. And basically, then these plates are sort of rolling along, literally like a conveyor belt, on these convection cells in the mantle, in the asthenosphere specifically. Again, the extent to which the lower mantle's involved, they're still a little fuzzy on, but yeah, that's what they got, and it makes sense. I have a little problem with the rising and relative, like I told you, you might have caught it, you might not have caught it. Some magma gets heated up and it becomes less dense compared to the magma around. Well, why didn't the magma to the left or to the right get heated up as well? That's where my brain goes. Because if it all gets heated up, well then it's all going to go up. I don't know. I have the same problem thinking about air and parcels of air. That's why if you ever had any like weather lectures or conversations about weather, they always draw that little cloud because it's hard to picture an air parcel. Okay, there's no delineations out there. You know there's a cold front, you know there's a warm front, but we don't see a line usually, right? And the same thing is happening down here inside of the Earth. It's hard to distinguish what makes a cell. But, again, the folks that are in charge of thinking about this stuff, they all tend to agree on this. So I'm going to defer to their intelligence in this area. But I do, of course, raise my hand every so often and say, wait, that doesn't make sense. So they're working on it. All right. And most of it does make sense. The other big glitch I have with it is why, after thousands of miles from the Mid-Atlantic Ridge to the west coast of North America, do those wheels change a little bit and go the other direction? So they're working on it. They're working on it. Let alone the hunk of rock that you saw. I'm not going to go back to it again, but you notice Australia and India were on that same color swatch, okay? And we several times told you that India used to be attached to the center east of Africa. So what the heck made that plate kind of back up and then turn? That's some crazy movement. So I think they'll modify this over the next couple of decades a little bit. I don't think the fundamental mechanism will change much, but neat stuff. Neat stuff. And again, I apologize I don't have a video of a lava lamp going on here. That would be something to add. All right, so that, my friends, is plate tectonics. And that is a whistle pig, as they used to call him back home. But that is plate tectonics, and that's going to lay the groundwork for us to move forward to earthquakes. Again, this semester, I did squeeze in a little bit of beginning of a water conversation, and we will, once we finish earthquakes, get back to that and do as much as we can about streams and or groundwater. But for right now, I wanted to make sure we got plate tech and earthquakes done. So when we come back on Tuesday, we'll be doing earthquakes. For those of you that like to read chapters, that's where we're headed. Awesome.